Hi kids, this video is on conservation of charge, which is the newest conservation principle that we're going to talk about, and the concept of charging, which is moving charged objects around inside of systems. The essential question for this video is, how do objects end up with an unbalanced sigma charge? So as we mentioned in the last slideshow, there is a new variable known as charge. And the symbol for charge is going to be a lowercase q, which is not super intuitive, but the unit for charge is the coulomb, which is a capital C, and that one does sort of seem like it makes a little bit of sense with charge. It turns out that the vast majority of the subatomic particles in our universe that have this property of charge are protons and electrons. There are a few other weird random subatomic particles that are charged as well that you'll learn about in sort of future physics classes, but for our class, the only charged particles we're going to care about are protons and electrons. As we mentioned in the last slideshow also, we're going to assume that protons have a charge of +1 coulomb and electrons have a charge of -1 coulomb each. That's actually not strictly speaking true. They actually have a charge that is less than a coulomb, but to avoid having to do math with really tiny numbers, we're just going to make this assumption. It is true that they have the same amount of charge, equal and opposite amounts of charge. So conservation of charge is the fourth big conservation principle that guides how physicists sort of picture the entire world and the laws of physics. We already had conservation of mass, conservation of momentum, conservation of energy, and now we learn that charge is another conserved variable. That means that the total, or sigma, charge in any kind of closed system is going to be conserved. Same amount before as it had after. In the system of our universe, it turns out that there are exactly as many protons as there are electrons. This is actually one of the great mysteries of science. There's no reason why the universe should have had exactly balanced protons and electrons, but it turns out that if it wasn't true, stars and planets never would have been able to coalesce. Life wouldn't be possible as we know it. So it's very convenient that we have the same number of protons and electrons, even if we have no idea why it ended up that way. In any case, the sigma charge of the universe is 0, because for each proton there's one electron, and those charges are equal and opposite. So the universe is a system of charges that have a total charge of 0. Smaller systems, of course, might not be balanced. They might not have a sigma charge that's 0. The way you can find or calculate the sigma charge of any system is just the total charge of the protons, which will be positive, and then you add the negative charge from the electrons. So for example, if we have a system of 4 atoms down there, 3 of which have electrons and each of which has 1 proton, the sigma q is +1 coulomb. We've got 4 pluses and 3 minuses, so this is an overall small positively charged object. That system in the middle has 4 atoms, 4 protons, and 4 electrons, so it's +4 -4, so we would call this a neutral sigma q, or a sigma q of 0 coulombs. And this last system is got 4 positive protons and 7 negative electrons, so this would be a -3 coulomb sigma q charged object. We would call this a negative charged object with a relatively large charge. The rest of the slideshow is going to be concerned with processes in which objects push and pull charges near them, and there's a lot going on in this slideshow, so if you are watching this because you missed class, please do take your time and listen and try to understand what's happening in the drawings as you watch. So the first process to talk about is called polarization, and polarization is not actually charging in that an object doesn't gain or lose any electrons during this process. What's happening is the electrostatic force is just pushing or pulling on the charges inside another object, even without making any contact or without causing those charges to move on or off. So for example, if I have a charged object on the left and I on the right, I have a neutral object. It starts neutral. When that negative charged object comes close to that neutral object, what's going to happen is the electrons, which can move, are going to try to get as far away from the negative charged object as they possibly can. Right? These electrons are being repelled from that negative charged object because they have the same charge. The protons in this neutral object are attracted, but they can't move because the rule is protons are stuck in the nucleus. So those protons stay where they are. They're all going to be experiencing forces in this direction, but they don't actually get to go anywhere because that's sort of the rule about protons. Interestingly, even though this is a neutral object, this neutral object is going to be attracted to the negative object. And the reason is because when you polarize, it's essentially like having two halves. We've got this negative half on this side with all the extra electrons and a positive half on this side with all the extra protons. And they're stuck together, but you can still treat them like two separate objects. We've already discussed the positive half experiences an attraction and the negative half experiences a repulsion. But because of the inverse relationship between distance and electrostatic force, it turns out this force, this positive attraction, is actually a bigger force than the negative repulsion because this half is actually closer than this half is closer and this half is further away. So even though we've got this neutral object, it's going to be attracted. And that's true regardless of what the charge of the other object is. If this object was positive, everything would happen in reverse, but it would still end up with an attractive force because the half that is closer is going to be pulling stronger than the half that's on the other side. So the rest of the processes we're going to talk about are called charging, and the word charging means there actually fundamentally is some transfer of charges. The sigma charge of systems is going to be changing over time. Typically, most objects around you have balanced charges. So, as you look around the classroom or your bedroom, everything has the same number of protons and electrons. So you don't get charging just by touching things around your room because you already balanced and so are the other things around you. There are ways, however, to move charges from one object to another. Always by moving electrons because protons cannot move. So when you move electrons, an object's sigma q is going to be changing. If you lose electrons, you're going to become positive, and if you gain electrons, you're going to become negative. Just a reminder, we can't move protons during this charging process because moving protons would cause a nuclear explosion in the object that you're charging. So there are three main processes by which objects become charged. The first is known as friction charging, and this is probably the one you're most familiar with from your life as well. In friction charging, when you rub two different insulators together, electrons will transfer from one to the other. So if these are two different insulating materials, you'll notice they've got the boundaries drawn on there because they're insulators. That just means that the charges can't move around from atom to atom within the boundaries or within the material. But if you bring those things close to each other, they actually can move, they can be pulled off kind of like Velcro from one object to another. Those two objects were neutral to start, but as you rub them together, the green object, it turns out, just didn't like electrons as well as the orange object was. It was a material, it was like a particularly sticky Velcro, orange one there. And so as you rub the two surfaces together, the orange protons are going to steal off those those electrons from the green one. And when you look at the sigma charge of these systems, this one started off neutral, and you'll see the green became positive 5 because it lost 5 electrons to the orange one. And meanwhile, the orange one became negative 5 coulombs because it gained the same 5 electrons. So you will notice that if you add these guys together, the system is still 0 coulomb charge. We're still practicing conservation of charge in the system as a whole. The electrostatic series is just an experimental table that scientists have figured out which materials tend to steal electrons in this friction charging process. So there are some materials that really, really love electrons, and when you rub them on things, almost regardless of what you're rubbing them on, they're going to grab electrons. So for example, rubber has got a really negative affinity. It really, really likes negative charges, so rubber is going to grab electrons from almost anything. And down here on this other end, things like glass actually don't hold strongly to their electrons, and they're willing to give up electrons. So these things end up becoming positive when they rubbed on stuff, and these things at the top end up becoming negative. So it all depends on the material and how strongly it is attracted to electrons when you are trying to determine who becomes positive and who becomes negative, and even how positive and how negative they become when you rub together. The second kind of charging is known as contact charging, and this happens between two conductors that have unequal or unbalanced sigma charges with each other. When they're brought into contact, the electrons are going to basically equalize out from one conductor to the other, because in conductors, electrons can flow anywhere they want to go. They're not stuck near their atom. So if we have these two systems of objects, one with a charge of positive 6 extra protons, and the other with a charge of positive 2 with 2 extra protons, when you put them together, you'll notice the electrons basically spread themselves out to have the maximum spacing. They're going to move around until they have the same amount of charge on each object. So in this case, we have an after charge of positive 4 coulombs for each object. And the way you got that way was that one that was positive 6 gained 2 electrons, so that means it got 2 more negative, and now it's positive 4. And this one that had a positive 2 lost 2 electrons, and so now it's also a positive 4. Charge in these whole systems is conserved, conservation of charge. We still have 8 coulomb over here, and we still have 8 coulombs over here, so we haven't created or destroyed any charges on their own. A process that's sort of similar to contact charging but not quite the same is known as grounding. You may have heard of that before. The word grounding refers to connecting an object to the earth, the ground, like literally taking a wire from your house, as it's shown here. And this bottom little hole, if you've ever wondered about that from your electric socket, is called the ground hole. And that there's a wire connected to that just goes out to your house and into a rod into the ground. And the purpose of that is basically to neutralize things in general, because the earth is such a huge, huge, huge object that it can absorb extra electrons from objects that are negative, or if an object is positive, the earth can provide electrons to balance it out. So grounding in general means connecting an object to the earth. Often grounding causes things to become neutral, but not always, as you'll see in the last kind of charging that we're going to talk about here in a minute. So the last kind of charging is clearly the most complicated, but it's also the most industrially useful, so it's one that's worth learning about. It's known as induction charging. Induction charging uses those little mini processes we've learned about, polarization and grounding, to give a conductor an unbalanced charge, even without touching it to any other kind of charged object. So here's the way it works. You start with some sort of neutral conductor. This is the object that we are wanting to charge up. And you bring a nearby charged object into the scene. So I brought this negatively charged rod nearby this uncharged object, and you'll see that the first thing that it does is it polarizes. So if this is negative, we're going to have the electrons moving to this side. This diagram shows the protons moving. They don't actually move, but the left side would end up positive when the right side becomes negative. The next step is to attach a ground wire from the conductor to the ground. And the reason you do that is because electrons now can flow on or off of the conductor in order to try to get closer or further away from this charged object. In this case, it's a negative charged object, so the electrons on the conductor are going to run away and they're going to go onto the ground. So now when you remove that ground wire and eventually move your negative charged object away, you're left with a positively charged conductor and some extra electrons in the ground, but the Earth is so big that we don't tend to notice these very much because they're going to spread out through the whole Earth. So this was a process by which we made this object that started off neutral became positive even without having to touch it to this negatively charged object. We touch it to the ground, which is also neutral, but we don't have to touch it to any of our charged object. This is the process, if you've seen those new induction charging phones where you just set them on a pad and they get charged up. They're using a similar method to get charged without having to be actually touched or plugged in. This slideshow should bring up a bunch of sort of interesting level 4 questions for some of you guys that have some extra time on your hands to think about. The first is, does each kind of charging represent an open or closed system for mass? What is your evidence? So think about the 3 kinds of charging. Some of them are open, some of them are closed, and what would you use as evidence about those? And the second is, in each kind of charging, are the 2 objects involved going to be attracting or repelling each other after they're charged? And then the last question, if you really want to test yourself to see if you've got this, is run through that induction charging example that we just did, except instead of using a negatively charged object, try using a positively charged object and see if you can figure out where are the electrons going, what's happening during each of those steps. That would be a level 4 kind of processing to figure that out. Okay, I know that was a long one. Thanks for listening. And take a few minutes, if you can, to revisit the essential question, which is, how do objects end up with an unbalanced sigma charge?